Welcome to the tutorial on ANOVAs. Analysis of variance, or ANOVA, is a test of difference between three or more groups or independent variables. And so an example of that might be looking at study time for the national counselor exam. You could have a group of people who studied 4 hours, one that studied 8 hours, one that studied 12 hours, and your dependent variable would be the actual exam score, the NCE score. Or I might study first, second, and third year doc students on their research confidence, or maybe students in a stats class on their statistical knowledge, the dependent variable, looking at people in their week 0, week 4, or week 8. Now, in the first two examples I gave you, those are comparing groups, and they're only being tested once. In this last group, it's the same people being tested more than one time. So in that situation, we have what's called a repeated measures ANOVA. Now, this technique is called analysis of variance because we're looking at the variance between groups and within the groups. So you'll see what that means as we move forward. Now, with an ANOVA, you get an F score, and so it's called an F test. And like I said, there's different ways to do ANOVAs. First, we're going to be looking at simple analysis of variance, or one-way ANOVAs, but we'll also be taking a look at factorial ANOVAs, ANCOVAs, and MANOVAs. I created this chart here to help know kind of when do you use an ANOVA. So in this situation, if we have an independent variable, we have one independent variable and one dependent variable, we're going to use a one-way ANOVA. If we have two or more independent variables, ways that we're dividing the groups, then we'll have a factorial ANOVA. And if we have more than one dependent variable and one or more independent variables, we'll use a MANOVA. So again, just to stress, we need to have one dimension of treatment, which is your independent variable, and you need to have at least two levels of grouping factors, and you need to be looking at the differences across those groups. The formula seems pretty simple, although it takes a lot to get there, and that is F equals the variance between and divided by the variance within. As the F score increases, it's more likely to be due to something other than just chance. We have assumptions for ANOVAs, just like every other statistical process. We need to have an independent variable that's categorical, nominal, so that it can be broken into groups. We also need to have a dependent variable that's continuous. Now, a common thing that happens in social science is people will use a Likert scale in order to score something, and then they will treat it as if it's continuous. So if you have a Likert score, it is not unusual to see it used in an ANOVA, but it's not the best statistical practice. In fact, one of our examples we're going to use tonight is a Likert score that is used as a continuous scale. There are other tools out there that might be better uses and better ways to analyze that ordinal data. But for today, we're going to be looking at some data that is going to be ordinal, but we'll treat it as scaled. Not uncommon in social science, not the best way to do it, but it's done quite often. Our groups have to be independent of each other, so mutually exclusive. Our dependent variables should be normally distributed. There should be no significant outliers, and there should be homogeneity of variance between the groups, so they need to be somewhat alike. The first two assumptions are controlled by the use of an appropriate research method like quasi-experimental. And the last three assumptions, if they're violated, there is a non-parametric equivalent, Kurzweil-Wallace, that can be used instead. So let's take a look at one-way ANOVA. As I mentioned, a one-way ANOVA is a test of three or more groups across one independent variable and one dependent variable. In this particular example, we're going to look at a study done by the noodle company, who wants to know what thickness of noodle consumers like the most, which they find the most pleasing. Now, on this scale, it's 1 to 5, with 1 being the most pleasing. So the food manufacturer puts it to the test, and they want to see which one's going to be the most liked by the consumers. Now, a note about the survey. You'll note that 1 is the most pleasing. This is a little bit counterintuitive the way we think. Most of us think about surveys in the sense that the higher the number, the better it is. So in this particular situation, the way they set up the survey makes it a little harder to interpret, and you have to be a lot more intentional about your interpretants because it's not what you're going to naturally think of when you see these numbers. So the lower the number, the better. The higher the number, the least pleasant it is. So let's take a look at the Noodle data set from JASP. So I'm going to bring that up. So here's the Noodle data set in the class data sets. And you can see that this is set to ordinal, but thickness is really nominal because it's 3 groups. And I happen to know, I'm going to click on this thickness. I know that the first one is thick and that the second one is medium. So this is the size of the noodle. And the last one is the thin. Okay, so I'm going to change those so that it makes more sense than 1, 2, and 3 for me. All right, now pleasantness is currently listed as an ordinal number, which in reality is actually correct. It is ordinal. We're going to set it to scale because we're going to use an ANOVA to compare these groups to see if there's differences. Now, I am fully aware that these are ordinal numbers and that they are not equally distanced apart, and this is not the best use of the statistical analysis, but for the purpose of the data set and the example, we're going to pretend like these are scaled. We're going to go to ANOVA. We're going to click Classic ANOVA. And our thickness is going to go into our fixed factor. Think about this as our fixed group. So factors are groups in statistics. And then we're going to put pleasantness in our dependent variable. When I look at this data, I can already see that I have a significant finding because if I play this out, it's going to be 0.00000037496, which is far less than p-value equal to 0.001. So this is a significant finding. It is less than 0.05, so it is a significant finding. So I can reject my null and say there are, in fact, differences between the groups. This is a pretty large F score, so that doesn't surprise me. And you'll see that it gives you some additional information, which we'll talk about in just a minute. And so we're going to go back out and we can get some descriptive statistics. We can get our effect size, which will be important if we have a significant finding, which we do. Under model, we don't need to change anything there. Under assumption checks, we do want our homogeneity test. And we can get our QQ plots to see the linear regression. I don't think there's anything under contrast. No, border street, post hoc. So post hoc are important because with post hoc test, we are going to be able to see where the differences are. This model over here, the ANOVA table or source table as it's called, tells us that we have a significant finding, but all that tells us with an ANOVA is that there is a difference. It doesn't tell us where the difference is. These post hoc tests are going to tell us where the difference is. So we're going to move thickness over here so that we get some post hoc. You can do Tukey. I also like Bonferroni. That's one of my favorites. So I usually click that one. And then we can also display our error bars with a 95% confidence level. And that's all we need for right now. If we wanted to run our non-parametric, we would have a non-parametric here. We don't know if we need that yet or not because we've got to see what our normal distribution and to see if any of our assumptions are violated. So again, just a quick look here. These are our results. This is our effect size. This is our significance level. This is our score, our F test or obtained value. Here we have some descriptives. We know how many of each one of these responses we had, what the mean result was, remembering that the lower the result, the more pleasant it is. We have some assumption checks. With the Levine's test, we want the p-value to be greater than 0.05 to show normality. So this is good. We can also see a pretty strong linear relationship here. And then on our post hoc, what we're going to look for is to see which one has a significant p-value. And we can see that thick to medium, there is no significant difference. So we can ignore that one because both of these exceed 0.05. And you can interpret this one or this one. You see they're really not that different. Whereas thick to thin, there is a significant finding because this is less than 0.05. And the same for medium to thin, which is less than 0.05. Now, why is there nothing here? Well, this just means that you carry it down. So this is thick to medium, thick to thin, and then medium to thin. So these are called pairwise comparisons, and this is part of our post hoc. So with ANOVAs, we have really a four-step process. We check our assumptions, we run the ANOVA. If the ANOVA is significant, we check for our effect, and if we have a significant finding, we also run post hoc. If we do not have a significant finding and we fail to reject the null hypothesis, we do not need to run an effect size or post hoc because there's no difference. We would only run the effect and the post hoc if there was actually differences in our data. So let's look at the write-up. Okay, so one-way ANOVA, and let's go through this. So I walked you through how I divided this up. I also did the descriptive statistics, checked our homogeneity. So these are all the steps that I took. All right, so now let's look at our assumptions. Step one. So for an independent ANOVA, the independent variable must be categorical. That was the thickness. The dependent variable must be continuous. That was our pleasantness, both met. The groups for both, they have to be independent. Yes, you couldn't be thick, medium. You had to be thick, medium, or thin. You couldn't be one of two. Dependent variable should be approximately normally distributed. We saw that in our QQ plot, which is right here, where it looks pretty normally distributed across that line. And then there should be no significant outliers, which we check with box plots. I'll show those to you in a second. And then the homogeneity of variance, we want the Levene's test to be non-significant result, which it is. This is a non-significant result, so that indicates homogeneity of variance. All right, so see how I report my Levene's test here? It's not significant right here. And then for my QQ plots, I say the QQ plot showed the data appeared to be normally distributed and linear. So how do I interpret those assumptions? Data set met all necessary assumptions. The IV was this and this. Groups of thickness were mutually exclusive. The QQ plot demonstrates normal distribution and linear. Data does not appear to have any outliers, and Levene's test showed the homogeneity of variance is not significant, and I reported that. Okay, you can also see outliers here. If there was like things scattered here, you'd see outliers here. Okay. Did I do, let's see. I can also do I have to use descriptives. Just trying to see if there was a way to do box plots from this one. Oh, error bars. There's our error bars. So let's take a look at those. So did they come up? Oh, you have to move thickness over to the horizontal to do for it to do the error bars. There they are. So if we had outliers, they would show up outside of these whiskers. So we don't see any outliers showing up here. There's no dots above or below these whiskers. Okay, so that's how we do it. So we have to move that over to thickness to the horizontal axis because that's what we're doing right here. And then it's going to automatically put the dependent variable here. And then we have our display error bars right here. You can also do descriptive statistics as we've done in the past, where I move pleasantness over and I split it across thickness. All right, so now it's giving me this data. And remember here, I can do box plots under customizable plots, and I can say label outliers. And then it will do that as well. It's working on it. There we go. So, and again, I don't see any outliers on any side of this. So that's another way to check for your outliers. All right. So now let's interpret our ANOVA results. As I mentioned, We have this significant p-value, and we have our descriptives. This is this p-value right here. When I take it to the exponential of -7, this is what the actual number is. So in this particular one, I can say the test statistic, this is like a formula here. Test statistic symbol, which in this case would be F, the degrees of freedom, my attained score, the p-value, and then whether it was two-tailed. This one was two-tailed because I said there's no there's no difference between the groups. So here's how I would report this. F, and then my degrees of freedom is the numerator is 2 and the denominator is 57. So 2 comma 57, this is subscripted, equals 19.3981. And then because this is such a large p-value, or really a tiny small p-value to be actual, it's just large to write. I would say p less than 0.001 because this number is less than that number. And because I said there was no difference, it would be a two-tailed test. So interpretation, the three groups of noodles, thin, medium, and thick, resulted in differences in pleasantness. I give my test statement, my outcome statement. Medium noodles were voted the least pleasant noodle with a pleasantness mean rating of 3.35, followed by thick noodles with a pleasant mean rating of 3.20. Thin noodles had a pleasant mean rating of 1.8. Now, while I can assume where the differences exist, all I can do here is really describe the differences. I'm going to have to go deeper into my analysis to really understand those differences. So first I'll check to see if it's meaningful. And I've run the effect size, and I've gotten these two effect sizes. For the purpose of this one, I'm going to interpret my eta squared, which is this little squiggly n squared, and that's 0.405. And so when I'm interpreting the effect size of ANOVA, this is how I do it. So in this particular case, this is a large effect. So the study had a large effect, and I report my eta square. So it does have, because it says right here, it is a significant finding. I also want to run my post hoc. It's going to tell me where my differences are. So again, I can interpret the Tukey or the Bonferroni. Doesn't matter which one. They're very similar, as you can see. And I'm going to interpret those. So the post hoc were conducted using Bonferroni and Tukey corrections. There's a significant difference in pleasantness between the thin and medium, right here, thin and medium. And I give the results for that. And in this case, I gave both. For thin and thick, same thing. There were not significant differences between medium and thick, and I gave the results for that. And then I explained with a mean difference of 1.4, thin noodles were voted more pleasant than thick. So this is the thin to thick, and here's that mean difference. And with a mean difference of 1.55, the thin noodles were voted more pleasant than medium. And you can see, again, the lower the score, the more pleasant it was. It's a little quirky to try to interpret that. I can also look at the error bars like I showed you. So these are my error bars to provide a graphic finding of these results. So you can see this one doesn't cross over these guys at all. So it's another visual check. These two overlap. See how this one is in the same space as this one? So there's not going to be a significant difference, whereas this one doesn't cross either one of these. So I'm pretty sure this is going to be a significant difference. So here's all of that put together. This is my interpretation for the ANOVA. So I've gone through and done my assumptions. I've reported my results. I've reported the effect size, and then I've reported the post hoc. All right. So join me for the next tutorial where we'll look at 3 groups of preschoolers and their language score.